So a dozen works very well on our scale. No one wants to say, give me 48 donuts. You'll say, give me 4 dozens of donuts. Or give me 3,000 sheets of paper. No, you'll say, give me 6 reams of paper. But on the atomic scale, these numbers are too small. But we have a number. We have something called the mole. And the mole simply means, on the atomic scale, is you have a number of atoms. So anytime we say the mole, we mean 6.022 times 10 to the 23rd items, not atoms for now, because again, it just generally means you have this many items. Sometimes this number is written as 6.02 times 10 to the 23rd for simplicity. So this is called Avogadro's number. So again, why is this number so huge? The dozen, that's a big leap. You go from a dozen all the way to something on the astronomical scale. Huge. Well, the atom is so small, that's why. So you cannot count individual atoms. So we have a number for them that's 6.02 times 10 to the 23rd. So anytime from now on we say 1 mole of oxygen atoms, we mean Avogadro's number of oxygen atoms, which is 6.02 times 10 to the 23rd. Nitrate ions, or even Geno's East deep dish pizza, 6.02 times 10 to the 23rd pizzas. Now, here's a stunning fact, is that if all kitchens in the world, restaurants and household, were making pizza at the same time, it would take them thousands of years to make this many pizzas. So again, we're going to deal with this number as a counting unit for the atoms. The atoms are so small. So what is the utility of this? Well, let's go with an analogy. So imagine you have a child and you want to play this exercise with them, and by determining how many jelly beans are in this jar right here. And you have, let's say, multiple jars. Well, you can count them if you have all day long. Let's say you have 7 jars, right? Take a long time. Or you can go with an exercise like this way. Let's say, I pick out your jelly beans and I'm just going to weigh one of them. All the other ones are roughly weigh the same. Atoms weigh the same unless they have, of course, those different isotopes. But the differences are very, very small. Let's say this gives you 5 grams for this jelly bean. So 5 grams is 1 jelly bean. Good. So then, to determine how many jelly beans you have, you probably know what you should do next, is you weigh. Of course, with subtracting, the weight of the jar, you weigh how many, or you weigh the sample of the jelly beans. So let's say you get 5,000 grams. That's the weight of the jar. So 1 jar weighs 5,000 grams. Well, how do we determine how many jelly beans we have? And that's 5 kilo, by the way. Remember those prefixes? All we have to do is take the 5,000 and divide by 5 grams. Why? You have 5 grams for the jelly beans. You take 5,000, divide by 5, and that gives you 1,000 jelly beans. So the idea here is we can count by weighing. We can count by weighing. And guess what now? If you know that 1 jar weighs 5,000 grams, which is 1,000 jelly beans, all you have to do now is count the number of jars. So if I have 7 jars here, then this would be 7 times 5,000 grams, which is 7 times 1,000 jelly beans. So those numbers then become 35,000 grams, and of course, 7,000 jelly beans for 7 jars. Okay, how is that going to relate to what we do? So here's how it's going to relate. If I say for carbon, I have 1 mole of carbon. The 1 mole of carbon weighs 12.01 grams of carbon. And we know that 1 mole of carbon is equal to 6.02 times 10 to the 23rd carbon atoms. So then what I should do, just look at how they relate. 7 jars, that's how many? Here, let's say you have 1 mole. Or the 1 jar, I'm sorry about this one here. I'm gonna bring this one right here. And look at this one. Of course, it's gonna take a little bit just of thinking about them. 1 jar is 1 mole. We know that this jar weighs 5,000 grams. Here it weighs 12 grams. Again, the atoms are very small. 1,000 jelly beans, this is about 6.02 times 10 to the 23rd carbon atoms. So from now on, you don't have to go and count the carbon atoms because it's impossible. It would take us millions of years if we count 1,000,000 atoms every second to count those atoms. What you can do now is you can just simply count by weighing. So if you say, give me 7 moles of carbon, then that would be 7 times the mass of carbon, which is of course 7 times, and let me put this in parentheses, 6.02 times 10 to the 23rd carbon atoms. So that's what we're going to deal with now, is again, being able to work with the mass and of course the corresponding number of moles. Now you might be wondering, where did I get this number from? Well, this number comes from the periodic table. So let me show you. If we look at our periodic table, this is what we call the atomic mass. Right here, if you look at the periodic table, here's the atomic mass right here. It's always the number on the bottom. So if we have carbon right here, look at this number. Now this number, of course, is the atomic mass, and we looked at the unit last time, and it was AMU. So AMU is on the atomic scale. It's 10 to the negative 24. That's how small it is. But we can scale up when we scaled up to the grams. So the molar or the atomic mass is, again, we're talking about the weight of that atom. But again, on our scale, we have to scale up. This is too small. But nevertheless, this is where we get the number from. So if we go back and look here, we can see that this number is right here, 12 grams. So we say, okay, let's scale up to our scale. And that would be 12 grams instead of 12.01 AMUs, which is equal to, again, 1 mole, and that is Avogadro's number of atoms. Now, you might be wondering about why do those atomic masses weigh differently? Why are they different? So for example, why is carbon 12.01 while magnesium is 24.31? If they both, again, if we have the grams, so here I'm going to write it down. This is 6.02 times 10 to the 23rd. Why are they different? Well, what do you think? You have more protons and neutrons. Look, I can have a dozen of an eggs and I can have a dozen of staplers. The number is the same, but their weight is different. Or a dozen of chairs, right? So if we go back here really quick, we saw that if we have a dozen of eggs, we have a dozen of bags of sugar, that the number would be the same, but what do you expect to be different? The mass. Same thing here. The mole of sulfur atoms is 6.02 times 10 to the 23rd sulfur atoms, and mole of iron would be an equal number of iron atoms, but they of course have different masses, as you see right here. So that from now on is called, and I'm gonna end only this video with this, is that from now on we're gonna call this the molar mass, and the molar mass is grams per 1 mole, or the grams, the mass of that atom equal to 1 mole. So the mass, the molar mass of carbon, and we look that up from the periodic table, that would be 12.01 grams per mole. If you say the atomic mass, then that would be, of course, in AMU. So here, I'll write it down here. The atomic mass of carbon would be 12.01 AMU.